Next, we're going to talk about the binomial probability distribution. This perhaps might be the most used probability distribution for discrete random variables. And the reason is because this particular probability distribution is used in situations where you have an event that has a binary outcome, such as success or failure, death or survival, pass or fail. And obviously there are many different types of other types of binary outcomes too. And so that's why this particular probability distribution can be very, very useful. Now, to help introduce the binomial distribution, I'm going to relate it to one of my favorite examples of where it's used, and this is with respect to field goal kicking in football. If you don't have a background in football, that's okay. Just realize that when a field goal kicker kicks a football, they are trying to kick it through what you could say is a goal. And if they make it in the goal, it's called a success. If they don't make it in the goal, it's called a failure. If it's a success, it's 3 points to the kicking team, 0 if it's a failure. Okay, so let's say that we have a field goal kicker, and they are going to attempt 4 different field goals, and all these field goals are going to be attempted under similar circumstances, such as, let's say, the same distance from the goal, the same weather conditions, the same type of surface that they're kicking off of, and so on. Now, with the binomial distribution, we need a certain number of, let's say, characteristics satisfied in order to be able to use it. And I'm going to relate this now to the field goal kicking instance here. In our particular case, we are going to have n different trials for each attempt at the field goal. In our case, there are going to be 4 different trials. So the first trial, success or failure for the field goal. Second trial, success or failure of the field goal. And there will be going to be 4 different identical trials, or 4 different identical experiments. With each trial, each time the field goal is attempted, either you have a success or a failure, or I guess what I ended up calling a made or a missed kick. Made is success, miss is a failure. Each trial, each field goal attempt needs to be independent of the others, meaning what happens on the first trial, first time the ball is kicked, can I have an effect on the second time that the ball is kicked? Can I have an effect on the third time the ball is kicked? And so on. And so if you're a football fan, you realize that maybe that might be questionable, because what happens on that first kick, the kicker might adjust then how they kick the second time or the third time, and so on. So that is somewhat questionable, but in order to use a binomial distribution, we need to have this independence, and you'll see where this pops up. There are things that you can do if you don't have the independence. We won't really talk about those much in our course, because in a general sense, even with field goal kicking, this independence is reasonably satisfied. Now, the probability of success at each trial or each kick for us needs to remain constant. And we're going to call the probability of success, just because it's going to be easier to note, we're going to call it pi, as in the Greek letter pi, not 3.14, but pi is going to be our probability of success. So then the probability of a failure on a particular kick or a particular trial in general would be 1 minus pi. And let's say for us that probability of success is 0.6. So you got a 60% chance of making the first field goal, you got a 60% chance of making the second field goal, and so on. And lastly, we're going to define a random variable y to denote the number of successful field goals. And this has 5 different possibilities. You could have 0, 1, all the way up to 4. So with that set up then, let's look at how we can find the probability that y is equal to 0, meaning that you have 0 successes out of 4 trials. So we're going to let G be the field goal is good or a success, M be the field goal is missed. And so the probability that y is equal to 0 means then that the first field goal is missed, and the second field goal is missed, and the third and the fourth as well. And this corresponds to what we had seen earlier in our course when we had the probability of A intersect B. Now, each trial, each kick is going to be independent of the other. And so because of that, if you remember when we had independent events, you could have the probability of A times the probability of B if you had independence. Well, the same thing works here. Now I can write this large joint probability there as the probability of the first is missed times the probability the second is missed times and so on. Also, because each time the field goal is kicked, it's done under similar circumstances, each has a probability of success of pi, then it doesn't matter if we're talking about the first or the second or third or the fourth. I can just write it as the probability miss times the probability of miss times the probability of miss times the probability of miss. Probability of success is pi. The probability of failure or miss is 1 minus pi. So notice that each of these probabilities is 1 minus pi. So I have 4 of them. So now I have 1 minus pi raised to the 4th power. For us, pi is 0.6. That means I have 0.4 left over. 0.4 raised to the 4th power is 0.0256. So overall, we see that the probability of missing all 4 field goals is quite small. Well, what about the probability that you have 1 success? Probability y is equal to 1. What would that be? Well, we could write it out as follows. It's the probability that the first one is good or successful, and the second is miss, and the third is miss, and the fourth is miss. That's one possibility. But you could also have a situation where the first is miss, but the second is made or good, third is miss, fourth is miss. And you can see also there are 2 other possibilities of where you make that 1 field goal. And so we need to find the probability of all 4 of these possible cases, sum them up. That's going to get us the probability that you have 1 made, or 1 is good. Then using the same techniques that we just did on the previous page, then, we can write this as, well, the probability of good times the probability of miss times the probability of miss times the probability of miss. Plus, then we do this then for the second case, we do for the third case, we do for a fourth case. And so we see a pattern here. Every single time then we're going to have one of these that are going to be probability of good or success. That has a probability of 0.6. And every single time also we have 3 probabilities of misses. And so if you combine everything together, look what we get. We get 4 times 0.6 to the 1 power, 1 meaning the 1 success or good, times 0.4 raised to the 3rd power for the 3 failures. And our overall probability ends up being 0.1536. We could do the same thing for probability 2 are made, probability that 3 are made or good, and probability 4 are good as well. And this is what we would get. And you hopefully start seeing a particular pattern with all of these. And that is that we're always going to write out in front, even though I didn't put it out here, we're always going to have out in front the number of different combinations of the M's and the G's, number of successes, number of failures. We're going to always write that out in front. And then we're always going to have then next the probability of success raised to the number of successes. Oops, that should be a 0, sorry. Times then the probability of a failure raised to the number of actual failures that occurred. And so with that then we can come up with a general expression for this particular case. And in fact, we can do for any particular field goal kicking or any other situation where these characteristics of a binomial probability distribution function are satisfied. And this is then what we get for a general representation for a binomial probability distribution function. f of y, again, since we have a discrete random variable, this means the probability that our random variable y is equal to a particular outcome, which we denote by little y, is equal to n choose y. If you're not familiar with what that means, I'll explain it in like 30 seconds, times pi, that's the probability of success, let's say in general for any kind of binomial application, raised to the y power, the number of successes, times 1 minus pi, the probability of a failure, raised to the number of failures power. And y can be 0 successes, 1 success, all the way up to n successes. And I think I said this before, but I just want to emphasize, very often in a general context, when we're talking about binomial distribution, our binary outcome that we can have for each trial is either success or failure. And pi is often referred to as the probability of success. Okay, so let's talk about this n choose y part here. What that's going to give us is that leading part in that binomial, in how we were writing out the probabilities to begin with. And what n choose y represents is what we call combinations. In other words, how many ways can you choose particular values of y out of n possibilities? In our particular case, how many ways can you have y successes out of n trials? Combinations are used outside of simply a binomial PDF. They're used, for example, in a mathematics area called combinatorics. And what n choose y actually represents here is n factorial over y factorial times n minus y factorial. So in our previous case, if we had n equal 4, y equal 1, what that means is I have 4 factorial over 1 factorial times 4 minus 1 factorial, which would be 4 factorial. 1 factorial would be 1. And then we have 3 factorial down below. I can cancel out the 3 factorial, and I'm left with just 4. There are 4 ways that you can have 1 success out of 4 possible trials. If combinations are new to you, at the very end of my notes, I do have a little bit of a more introduction to what combinations represent. I'm not going to go over that in our video, but I encourage you to examine it. The basic thing of what we need to do in our class is simply apply this result of what combinations give us. Okay, so this pi is a population parameter. So you can see how the probabilities from the binomial probability distribution will change as a function of pi. And so depending on what pi is, we're going to have different probabilities overall for the number of successes. And so this pi is going to be very important to us. And later we're going to talk about, later in the course, not in this section, we're going to talk about, well, how could we estimate it? Now, to do the actual computation for f of y in R, we can use a function called dbinom. You're going to see the same kind of syntax for other named probability distributions as well, where the name of the distribution that you're interested in, or some abbreviation of it, is going to be in a function like this. And then the d is always going to correspond to actually calculating this little f of y, the probability distribution function. This is for discrete random variables or continuous random variables as well. Now, well, what about the binomial CDF? Well, unfortunately, there's not a nice, closed form, nice expression like what we saw maybe with other examples. And what it ends up being is capital F of y. In other words, the probability y is less than or equal to little y. And it's the sum from t equals 0 to y, then my binomial PDF written in terms of t possible successes. And again, the reason why I'm using t there is so that one does not get confused with what we're evaluating this sum up to, which is our y that we're interested in. So let's say if I want the CDF for, let's say, 1 success, what that means then is simply I'm going to add my little f of 0 to my little f of 1. To find then this CDF in R, I can use a function called P-binomial. And again, you're going to see this with other name distributions. Whenever you're working with the CDF, you put the name or the abbreviation of the corresponding PDF that you're interested in this case a binomial, and to say that I want to find the CDF, I put a P out in front, which corresponds to probability. Now, there's a special case of a binomial PDF that often occurs in practice, and that is what's called a Bernoulli PDF. And simply, this corresponds to the situation where you only have one trial. And so, in other words, that combination that we saw up front disappears, and now where we had n minus y failures, now we have 1 minus y failures. Now, one place where this is used is, let's say that you have, you're doing a particular maybe kind of experiment where you do one trial. It can be a Bernoulli PDF can be used with it. And then you go do the experiment again with one trial. And then you do it again and so on. And so let's say that y1 is the random variable representing what happens on the first trial, y2 for the second trial, yn for, let's say, the nth trial, just to be general. Then if I were to sum up all those y's, call the sum w, w ends up happening to be a binomial PDF, where now we're looking at n choose w, pi raised to the w power, 1 minus pi raised to the n minus w power. Hopefully that makes some intuitive sense to you, that if I do the experiment as, let's say, n different sets of implementation, and as long as the probability of success is the same on each of those corresponding trials, and sorry if I didn't mention that before, then I get back the binomial. Okay, so let's take a look at how we can do some of this stuff in R. Okay. So again, D binomial allows me to get my f of y value, my little f of y. And so let's say I'm interested in 2 successes, 4 trials, probability of success in each trial is 0.6. So prob represents, prob in terms of the argument name in R, represents our pi, size represents our n, and x represents our y. So if I go ahead and run that segment of code, we get what we saw before, 0.3456 for that field goal example. I could do a whole bunch of calculations at once. So if I put 0:4 there, remember what that means for R. That means 0, 1, 2, 3, and 4. I can get all my probabilities of interest. And then if I wanted to use the, if I wanted to get the CDF then, let's say at y equal 1, remember what that's going to be is little f of 0 plus little f of 1. I can use those two things sum. I can use my p binomial function where I have the size argument, I have the prob argument again, and now instead of having an x argument, I have the q argument, which stands for quantile. And so if I run this code, the 0.179 quantile from a binomial PDF, or a population characterized by a binomial PDF, is 1. And again, you'll see the same kind of syntax in other places as we go along in this course. And so, you know, we haven't really thought of a CDF in terms of giving us the corresponding probability for that quantile, but in a sense, that's what it does for you. So again, what this is going to represent, just to make sure this is clear, is capital F, of 1. Now, of course, I could use the D binomial function with this for 0 and 1 and sum the corresponding results and get exactly the same thing. Okay, let me go back to my notes here. Well, how about we put together a nice data frame that displays the little f of y and the capital F of y together. So here's my data.frame. Y is going to be 0 to 4. I'm going to find little f of y using the dBinom function and find capital F of y using the pBinom function. And here is a nice display of the PDF and the CDF. Notice, for example, how this 0.1792 is the sum of the first two entries for f of y. We can also do a plot as well of the PDF or the CDF. Here's the plot for the PDF itself, and we've seen these kinds of plots in a similar manner before. So n's 4, y is going to be 0 to 4, pi is 0.6. I use my plot function to draw the plot. On my x-axis, I'm going to have all the possible values of y. On my y-axis, I'm going to have little f of y. And then I use the type equal h argument to say, hey, let's draw a line high. In other words, from on the y-axis, y equals 0, up to what I'm specifying for my y argument. So I'm drawing a line up high. X-axis label, y-axis label, I put a nice little title on the plot. A line width, we're going to make it 2 just so that the lines stand out a little bit better. Color is red, and I'm going to control how my y-axis is drawn from 0 to 0.4 approximately. And here's the plot. So as what we've seen before, f of 2 is 0.3456, and we can see that relative to the y-axis scale. Okay. Now, let's talk about, well, what does a population characterized by a binomial distribution actually mean in terms of like a sample? And so in R, what we can do is simulate what a sample will look like from this kind of a population. Let me get back over to my R program again. And to do this, we're going to use a function called rbinom. Again, you'll see similar syntax with other functions in R that allow you to simulate what a sample from a population looks like, where you have the PDF name and then R for random. And in this particular case, I want to simulate what a sample size 10,000 would look like. N is 4, pi is 0.6. I'm going to put all the results into an object called Y. Then I'm going to look at the head of it and the tail of it, the first 6 and the last 6 observations. And this is what I get. So for my sample, the first time I got 3 successes out of 4 trials. Next time, 2 successes out of 4 trials. Next time, 3 successes out of 4 trials, and so on. And my last one, 2 out of 4. Okay. Now, that's a random sample from the population itself. And if I were to run it again, I'm going to get different results. And if I were to run it again, I'm going to get different results again. Now, especially in a teaching circumstance, I would like to be able to reproduce the results so that what you see in my notes is exactly what I'm running on the screen, or is what you see in the screen. So my notes match up with my screen. That's what I'm trying to say. Also, in many research situations, you need to make sure your results can be reproduced. And for statistical research or other research, when you are, let's say, evaluating some situation that can be characterized by a binomial distribution, and you want to examine certain characteristics of it that you can control, and maybe perhaps it requires you to simulate a sample like this, you would like to be able to somehow always get exactly the same sample no matter when you run the code. And as you just saw here, 3 times I ran it, I got 3 different results, 3 different samples. So to be able to reproduce your results, to always get exactly the same sample, what I can do is what's called set a seed number. Without getting into all the background about how what's called random number generation is done, or in other words, taking a sample from a population characterized by a PDF. Basically, R or other software packages that do it basically uses what's called a seed to help start the simulation, the random sampling process. And if I set a seed right before I run the corresponding code to take the sample, I will always get the same results. So this particular case, I set a seed, and it can be any number you want. I just ended up choosing 8239, and let's see what I get. So notice the very first observation was a 1, the second one was a 3. Let me run the exact same code again, and I get the exact same sample. Okay, so that's what a seed number represents, and we will use that in our course. Well, let's summarize the information that's in my sample. So to do that, I'm going to use a function called table. And what this does, it gives me a table of counts. 263 times I got a 0, 1,510 times I got a 1, and so on. Let's find the proportion of times I got a 0, the proportion of times I got a 1. How do I do that? I divide by my sample size of 10,000. I could just simply put 10,000 here and said what I said, okay, let's just find the length of what's in y, which will be 10,000. And so here are my proportions. And let me come back over here to Word. And take a look at these proportions and compare them to what we had for the probability distribution function. In particular, f of 2 was 0.3456. Notice how that's so close to what we actually observed. And the reason why I'm pointing this out is, again, to give you a sense of what does it mean when a particular population has a particular probability distribution that can be used to characterize how items are distributed in the population. Here, this sample, we get results that are reasonable given what we would expect that probability because of that what that probability distribution function gives us. Well, let's look at some graphical displays of our sample that we got. So I could use the hist function to do a histogram. And unfortunately, with discrete random variables and their corresponding observed values, sometimes it can be not displayed very well here. So, for example, at y equal 2, I have a height here of 3,454. But notice this bar here is saying, okay, I'm actually getting values of, I'm getting 3,454 values between like 1.9 and 2. Well, when we know we can only get a 2. And so, to some respect, doing a histogram with the observed values of discrete random variables can be a little bit confusing, but you need to take into account what this discrete random variable actually means. Another way to do a similar plot is simply do a bar plot. So if I save my results from table into an object called save.count, I can use the bar plot function in R to do a bar plot where the height of the bars is going to be these counts. And then for each category, I'm going to give it a name, like 0, 1, up to 4. And for my y-axis label, I put a y. X-axis label, I put a y. And here we have a bar plot of these frequencies of what occurred in our sample. Well, in this particular situation for field goal kicking, what would we expect on average the number of successes to be? For the first time I run, I do 4 kicks. For the next time I do 4 kicks. For the next time that I do 4 kicks. What on average would you expect? Well, that's answered by finding the expected value of y. Now, in a general sense, where we don't define what n is, where we don't specify what pi is, the expected value of y is equal to n times pi. Why? Well, this goes back to how we defined finding an expected value before. Let's actually go through a formal proof of it. Okay, so to find the expected value of y, remember what we need to do is sum over all the possible values that y can take on. And for each time, we take y times f of y. And so that's what I've written out here. So what that means is I'm going to take 0 times f of 0 plus 1 times f of 1 plus n times f of n. Okay. So what I've done next, you could say this is, let's say, step 2 here. I've written out what that probability distribution looks like, multiply it by y. Now, in the end, excuse me, what we want is a final result n times pi. So how we do, I hate to say this, but let's say a little bit of a mathematical trick that's often done in these kinds of situations, where what I'm going to do is I'm going to factor out of the sum what I know what I want, n times pi. And then what I'm going to do is try to show that what's inside the sum actually sums to 1. So when I factor out n, notice I'm going to take the n out of this n factorial. So what am I left with? N minus 1 factorial. For the pi there, I'm going to factor it out of this pi raised to the y power. So what I'm left with now is just y minus 1 of these pi's. Okay. Next, notice when I have y equals 0, 0 times f of 0 is going to be 0. So like this right here, this is equal to 0. So what I can do actually is start my sum not at y equals 0, but y equal 1. And that's not going to affect anything. Next, I have a y here, and I have a y factorial here. Let's simplify. I'm going to put that y into that y factorial. What happens? I have y minus 1 factorial left now in that denominator. So it's like saying, okay, I have 4 and divided by 4 factorial. What's that equal to? Well, 1 over 3 factorial, because that 4 cancels out with that 4. I get a 3. Okay. Now I do something you could say is a little cool. Let's define a variable, call it u. That's going to be equal to y minus 1. In other words, y is now going to be u plus 1. And so wherever you see y in this expression here, I'm going to replace it with u plus 1. So for example, I have a y minus 1 here, replace it with u plus 1. What am I left with? U factorial. Also, in terms of my sum here, if I was summing before from y equal 1 to n, look what happens now. Because, excuse me, when y was equal to 1, that means now u has to be 0. So when y is 1, u is 0. Also, when y is equal to n, that means now that u has to be n minus 1. So notice how I changed how I'm doing this, what I'm summing over. And if you look at what's left here, this is a binomial distribution that's being summed, where I have u possible successes out of n minus 1 trials. The probability of success on each trial is pi. And so since I'm summing up that new PDF, that sum, of course, has to be equal to 1. And so now I have a 1 there, and that's how I do my proof. Expected value y is n times pi. You could do a similar thing with the expected value of y squared. And the reason why you want to do that is because then the variance of y ends up being n times pi times 1 minus pi. Okay. So hopefully, with respect to the expected value of y, of course, we could also denote this as mu. Hopefully, having mu equal to n times pi makes some sense. I'm going to, let's say, kick 4 field goals. Each time I have a probability of success of 0.6. So what would I expect as the average number of field goals that were made? Well, 4 times 0.6, or 2.4. And, what does Chebyshev's rule then says about what would be reasonable values of the number of successes? Well, again, Chebyshev's rule would say, let's say, take mu minus 2 times sigma, take mu plus 2 times sigma. Generally speaking, you would expect most number of successes to fall within this range. We have an example of showing how that occurs shortly. Well, while it's great to be able to do this kind of a proof by hand, you could also do the proof using Sage. So let's talk about how to do that. To do a factorial in Sage, there's a factorial function. So factorial of 3, which would be 3 times 2 times 1, is 6. In Sage, I need to declare what my variables are in Sage's terminology. I got something called y, I got something called n, I got something called pi. And so then I can define f of y using the n factorial over y factorial times n minus y factorial. Pi raised to the y power, 1 minus pi raised to the n minus y power. That's going to be my f of y. And just to show that indeed, if I were to sum over all the possible values of y, f of y, look what happens. I get 1. Then to find mu, I can take the sum of y times f of y. I'm going to sum over y from 0 to n, put that into what Sage calls a variable, mu, and look what I'm left with. Pi times factorial n over factorial n minus 1. In other words, pi times n factorial over n minus 1 factorial. For some reason, Sage doesn't know to simplify this to pi times n immediately, so you can tell Sage to do that by using what's called a method function in Sage. Mu dot simplify underscore full, you get the n times pi. On your own, please investigate how I found then the expected value of y squared and also the variance of y as well. Okay, so let's go back to our field goal kicking example. Again, the expected value of y, or mu, is 2.4. The variance would be 0.96. What Chebyshev's rule says is that if I take mu plus or minus 2 times sigma, the square root of 0.96, I get 0.44 to 4.36. So what that means is that you would expect your number of successes to fall somewhere between 0.44 and 4.36. Obviously, though, you can't have a 0.36 of a success, though, of course. But what that says, though, is that it would be very unusual to have a 0 as a number of successes in for this particular binomial distribution. And so relate that, though, go back on your own, and compare this to what we had for the probability of y equals 0. In other words, f of 0. Compare that so that you understand why that makes some sense. And so let's say that in an actual football game, a field goal kicker makes 0 out of 4 field goals, where they're all attempted under similar circumstances, and pi was 0.6. Based upon this information that we have with this probability distribution, what could we say about this kicker here? Well, we could say that, well, this was a very unusual occurrence to have happen. Maybe that kicker's pi is not actually 0.6. Maybe it should actually be something lower, so that it would be more reasonable to have y equal to 0. And so using that kind of logic then gives you some way of understanding how this probability distribution function can be used in practice. We will expand upon that same idea later in our course to make a more formal judgment. Now, let's go back to our sample that we had of all these 10,000 outcomes. If I were to find the mean of all those, I get about 2.4. If I were to find the variance, I would get 0.95. Notice how close those were to the expected value of y and variance of y. And again, what this does, it gives you some sense to understand what it means for a population to be characterized by a probability distribution function. What you get in your sample then corresponds to, or you would expect it to be similar to what actually is happening in the population itself. And to expand on that farther, we have some questions very similar to what we've seen before, where, will the sample mean tend to get closer or farther away from the expected value of y as that sample size increases? Well, the answer is it will get closer. Why? Because the sample is going to be more representative of the population. On your own, you should think about, well, what will happen with respect to if you decrease the sample size? That's a very good question to think about. But the problem, and without getting into all the details, because we will see some of this later, is that the sample mean can be now farther away from what we expect y to be, the expected value of y, or mu. It can get farther away. How much farther then will be actually quantified as we go along in our course. So let's actually look at some plots of a binomial distribution in general. I've set up this particular program here so that you can interact with it yourself, so that you can explore what happens with the binomial distribution for different values of pi, for example. And so what I've done here is I've set up the program where I've actually done some screen captures of plots for n equal 20. Let's say pi is 0.1. So these red bars that are going up represents what the probabilities would be, just similar to what we've seen before. And we can see with a probability of success of 0.1 on each of the 20 trials, our number of successes that we would observe will tend to be kind of small. That should make sense. And what we also see here is that notice how we have kind of a skewed distribution here. We've talked about skewness before in terms of histogram. If the histogram tends to have a longer right side to it, in terms of these bars tend to go out farther and farther out to the right in comparison to what happens on the left side, then you have what's called a right skewed distribution. Here, with respect to now a PDF, we have a right skewed distribution. Also on this plot, I plotted where the mean is. Notice how it's kind of in the center there. And also I plotted the rule of thumb using 2 standard deviations from the mean. And we can see that the most likely cases for what y will be as corresponding to these probabilities are within the 2 blue lines. So just to emphasize, this is at mu plus 2 times sigma. This is at mu minus 2 times sigma, or actually, let's say the max of mu minus 2 times sigma and 0. Since mu minus 2 times sigma could actually be less than 0, which wouldn't make sense for a binomial distribution. Okay. Now let's say that n is 20 again. Now pi is 0.25. So now we have a higher probability of success. Look what happens to the probability distribution function here. Now we have more, the most likely possibilities have a higher value of y to it. Look at now the mean's equal to 5. Also notice how the probability distribution function is becoming more symmetric. It is not symmetric yet. It is still right skewed, but it's a lot closer to being symmetric than the previous one. Then if we have pi equal 0.5, we do actually have a symmetric distribution. Notice now where this distribution is centered at, y equal 5. And if we increase pi even further to 0.75, now we're basically kind of having a mirror image of what we saw before with pi equal 0.25. And in fact, as we keep on raising pi up closer and closer to 1, what will happen is that the distribution becomes even more less skewed. Okay. Now, one of the key things to take from this plot is notice how the plot changes as a function of pi. And so it's going to be very important for us to have a good idea what pi is, and we will talk about that more later in our course. Some final notes. So a binomial distribution is used in a situation where the outcome of, let's say, each trial is binary, like success or failure. But there are other instances where you can have 3 possibilities for each trial, 4 possibilities. In that case, you can generalize the binomial to what's called a multinomial probability distribution. So one possible situation where this could occur is, let's say, you are looking at what political party affiliation a person has. And let's say that there's three: Democrat, Republican, Independent. In that situation, you could use a multinomial distribution with that. Another example that I recently came across in reading a paper is some scientists were interested in examining what kind of snack a person chooses after they do in a workout. And these people were given a choice between, the people that participated in the study, a brownie, an apple, or none. And again, you have three possible outcomes. A multinomial distribution could, and they did, use it with that particular situation. And one last note then. So one limitation of this binomial distribution is that it remains constant for each trial. So every time I kicked a field goal, I had to have pi equal 0.6. How could we maybe generalize the binomial distribution so that it wasn't dependent upon having exact same probability of success on each trial? Here's a little bit of information about how this can be done. Suppose we let pi be equal to this. So if you're a football fan, you know that probably the number one factor that affects the probability of success of a field goal is the distance. 20-yard field goals will have a higher probability of success than longer field goals, like 50-yard field goals. And so what we can do is build that distance into our expression for what pi actually is. And suppose I have a plus b here, which are actually parameters that I will want to estimate, times the distance. And so if pi can be written as a function of the distance, then I have a way to change pi for every single field goal that's attempted based upon distance. And we could generalize this farther. We could actually write it out like this, using E. Without going into all the details, what this will do is guarantee that for whatever value I choose for A and B, pi will be between 0 and 1, which of course we need since pi is a probability. And if I write out pi like this, I get what's called a logistic regression model. This is a very, very common way that people use to model binary outcomes. I talk about logistic regression a lot whenever I teach a course that deals with what's called categorical data analysis. Okay, so with that then, that ends the discussion. If you want to know more about combinations, I have some more information at the very end of our notes.